Good day, class. Welcome to lecture number 8. Today we will continue our talk on spatial filtering. If you remember, we studied in the spatial filtering, we have a sub-image which is called a filter, and this filter has its coefficients. In these slides, you can see the mask that we have, the filter that we have, and we show you what we mean by its coefficients, as you can see in this picture, which is from the Gonzalez and Wood book. This mask will operate in a neighborhood. If you remember what we mean by neighborhood, it means that we have, let's say, 3x3 mask, so we will put it on 3x3 neighborhood of an image, and we will do this operation, or whatever the operation is required. And the first filtering type that we will talk, and it is a linear spatial filtering, is convolution and correlation. Convolution involves calculating the weighted sum of a neighborhood of pixels. The weights are taken from the convolution kernel or filter. Each value from the neighborhood of the pixels is multiplied with its opposite on the matrix. Opposite on the matrix means that we have the rotation of 180 degrees. And this rotation of 180 degrees, if you remember from the convolution formula, comes from that we are flipping the, one of the functions that we have, because you can actually swap the functions. So this flipping means that we have to do the rotation in 2 dimensions 180 degrees. So here in these slides you can see the general definition or formula of the convolution. And the notation that we use for convolution is a star, as you may remember from the signal processing courses that you have taken before. Now consider 3x3 neighborhood. Given a convolution kernel or mask W, you need to rotate the mask with 180 degrees. So here in this slide we have the convolution kernel W, and we are seeing the rotation of 180 degrees. So it's like that the left top corner will go to the bottom right, and correspondingly we are rotating the other values. Remember, in this convolution kernel that we have in this example provided by Gonzalez and Woods, the weights can change. So based on the application we can have different weights. Some of the coefficients, some of the weights for some masks are fixed, and the mask have a special name. Let's say Sobel edge detector, it has, or Laplacian edge detector. It has its own mask with its own coefficients. So when times comes, I will tell you. But in case of the convolution kernel, the values can be changed based on the application. So now we have rotated with 180 degrees, and we have an input image. So we want to see what is the result of the convolution. What we do is we are putting the center of the mask on the pixel value that is of interest. So the center of the mask will be put on the pixel values that we have. And now we can see the neighborhood. And what we do, we are multiplying each coefficient by the corresponding pixels, and we add all the values. And by doing this, the first new pixel value is 5. We do the same thing for the next one, and we get the next value. And we have to continue this one for all the pixel values that we have. So the new image, the final output, can be calculated, and this is the result. Now, I have shown you in the slides a few of the calculations, but you can try to calculate the rest at home. Now, I said that we will talk about convolution and correlation. Correlation is nearly identical to convolution, with only one minor difference, where instead of multiplying the pixel by the opposite of the kernel, you multiply it by the equivalent of the kernel. In other words, we do not have the 180 degrees rotation. Or, if you look at the definition from the signal processing, and as you can see in this slide, we are not flipping the signal. We are not rotating the signal 180 degrees. So this is the only difference of correlation and convolution. We show it with the little o as a notation of correlation. So consider a 3 by 3 neighborhood this time. We are using the same kernel and we want to do the correlation. Same input image that we had before. We have the same kernel, but this time we want to do the correlation, so there is no need to do the rotation. And we do the same procedure. We put the center of the kernel on the pixel of our interest, and we define our neighborhood. We do the multiplication of the coefficients with the corresponding pixel, and then we add all the values. And as you can see, this is the image that we are getting. Correlation is used in order to see whether we have a specific portion of or a specific image inside the image or not. For instance, let's say you are looking for a letter, a character A inside a text image, and we use the correlation in order to find out this similarity. We will get back to this in the course of digital image processing, not necessarily in this series of video lecturing, but if you are taking the digital image processing course, we will get back to this point later. Now, continuing our talk on linear spatial filtering. We are using a 3 by 3 matrix shown in the previous slides, like convolution or the correlation one. And then what we were doing, we were multiplying each coefficient with the corresponding pixels, values in the neighborhood that we have. Here in this slide, you can see what we mean by corresponding pixel values. So each weight will be multiplied by the corresponding pixel value and it will be added up. And the result, the new pixel value, is calculated in that form. Linear spatial filtering is often called as convolution operation. And the filter mask is also referred as the convolution mask. So the convolution filtering is a very general term that we are using. The next operation that we will talk on the spatial domain image enhancement is smoothing spatial filters. Smoothing filters are used for noise reduction and blurring operation. Blurring can be used as pre-processing step for other image processing operations. There are two main types of smoothing filters: smoothing linear filters and smoothing nonlinear filters. Remember, we have talked about this smoothing or blurring operations before when we talked about sampling. We said that if we want to have an anti-aliasing filter, we have to use the low-pass filter, which is a blurring filter, which is a smoothing filter. Now, a smoothing linear filter or averaging filter. Note, this is not averaging the image, several of images. We have one image and we are using these sub-images, masks, in order to do the averaging. So the response of a smoothing linear spatial filter is simply the average of pixels contained in the neighborhood of the filter masks. These kind of filters are called averaging filter or low pass filter. So we are taking a neighborhood, we find the average of this neighborhood. Now here in this slide you can see two averaging masks that we have. One of them has all the weights equal to 1 and the other one is a weighted averaging filter. Random noise consists of sharp transitions in gray levels are very frequent to occur in an image. And in order to reduce these noises, we can use the aberration filter. So aberration filter has this specific application. If in this slide you look at the weights that we have, the coefficients which you multiply by this mass is actually the addition of all these weights. When we have a uniform filter, we see that, or a box filter, we see that all the values are 1, 3 by 3 mass, so it's 1 over 9 should be multiplied by that. And when we have a weighted average, if we add all the weights, it's number 16, so the mass will be, the result will multiply by 1 over 16. Here you can see an image and you see the effect of changing the size of the masks. The mask, the aberration filter, which is doing the smoothing, is also doing the blurring effect. As you can see, as we are increasing the size of the mask, we are causing more smoothing, more blurring effect. As here, which is from the Gonzalez and Woods book, when the size goes to 35 by 35, you can see it's quite blurred, but it's very smooth. So if we have some high frequencies noises, then they are all will be removed. The smoothing is actually used in order to segment out some part of an image. Here you see an image from the Hubble Space Telescope. And in the image in the middle, you see the image processed by a 15 by 15 averaging mass. And on part C, which is on your right, you see the result of the thresholding. In other words, after the smoothing, we are using the thresholding in order to convert the image into the black and white. Then, this one can be used as a general mask in order to segment out some part of the image. Now, today, we saw about how to use the spatial domain filters. We talked about the mask and kernels. We talked about the convolution and correlation. We have seen how to apply the averaging filter, box filter, and weighted averaging filter. And in the next lecture, we will continue our talk on image enhancement in spatial domain by using the statistical terminology. I hope that you enjoyed today's lecture. Read the extra materials that we are providing in the website, and be seeing you.